This is 10.1 Sequences and Series. Sequences and series are often useful in modeling sets of values in order to identify a pattern. A sequence is an ordered list of numbers. An infinite sequence is a function where your domain goes to infinity. And a finite sequence is where it has an end, so it has a start and a stop. And the values, or the range, the y values, are called terms of a sequence. There's two kinds of formulas that we're going to use to describe a sequence. One is an explicit formula, which gives you the nth term of a function as a function of n. You can find any term. So equations such as a sub n equals 2n plus 1, I can find the first term, I can find the 9,000th term. I don't have any restrictions on what term I can find. On number 2, a recursive formula gives you the nth term using the preceding term. You can only find a term if you know the previous one. And we're going to do a couple of those in a minute. So I want to find the next four terms of the sequence. So this one should be pretty easy. You just have to figure out what the pattern is. So if I look at each one of these, I'm adding 5 every time. And let me change my pen width. So if I add 5, 17 plus 5 gives me 22. Add another 5, I get 27. Add another 5, I get 32. Add another 5, I get 37. So those are my next 4 terms of my sequence. So you pretty much just, in this first section, have to figure out what the pattern is. I want to find the first 4 terms of a sub n equals negative 1 to the n over n times n over n plus 1. So this is slightly different. It's not as easy and obvious to do. So the first thing you're going to want to do is you're going to want to start with 1. And a sub 1 basically means first term. So if you look, let me find a different highlighter color. Anything right here, oops, let me undo that. Okay, let's try that again. So I don't think I have a highlighter here, but basically any place you have an n, here, 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 and here, you're going to fill in 1, and then you're going to fill in 2, and 3, and 4. So my a sub 1 is negative 1 to the first power times 1 over 1 plus 1. Negative 1 to the first power is just negative 1 over 1/2. So my first term is negative 1/2. So then if I do the next one, a sub 2, do a negative 1 squared. So any place again that I'm putting an n, so that's a sub n, the n for the exponent, the n here and the n here. Anywhere there's an n, I'm going to put in 2. 2 over 2 plus 1. And after a while, you'll figure out what the pattern is. Negative 1 squared, let me change this term, is going to give you a positive 1 to the 2/3, or sorry, times 2/3. Gives me 2/3. That's my next term. Let's change pen color. Third term, negative 1 cubed. You're going to do a lot of plug and chug in this chapter. So I would get used to it. And a lot of just doing regular old plain addition. So you can kind of see before we finish and do the rest, you're going from negative to positive to negative. That pattern you get by doing negative 1 to some power. And we'll talk later on. This one starts with negative. So if you want to go negative, positive, etc., start with a negative, you're going to do negative 1 to the n power. If I want to start with a positive number, then that n has to be either an n minus 1 or an n plus 1 or an n plus 3, n plus some odd number in order to make this exponent either 1 less or 1 more so that it's an even number and it becomes positive. But we'll do one of those later. And if you notice any of your other patterns, the top is just 1 less than the bottom. So without even writing out all my work, my 4th term is going to be positive 4/5. And I actually can keep going and find everything else now that you see a pattern to it. Okay, I want to find the next 4 terms of this sequence. And you'll notice that I have an a sub n and an a sub n minus 1. So this is going to end up being recursive. So I'm end up going to think of a sub n as your current term and a sub n minus 1 as your previous term. But I'm just going to show you mathematically. So I already know a sub 1 is 1. So we're given that. So I'm going to find a sub 2, which means I'm pretty much just going to plug in 2 for this n, 2 for this n, 2 for this n. So that's a sub 2 minus 1 plus 2 times 2, which 2 minus 1 is 1 plus 4. And we already know that our first term was 1 plus 4 gives me 5. So my second term is 5. Third term that we're going to find is a sub 3 plus 2, 3 minus 1, 2 times 3. So a sub 2 plus 6. And we already know that our second term was 5 plus 6 gives me 11. Fourth term, a sub 4 minus 1 plus 2 times 4. That's a sub 3 plus 8. And we already know that our third term was 11 plus 8 gives me 19. And so on this, so one more, a sub 5, you're taking 5 minus 1 plus 2 times 5. That's a sub 4 plus 10. And your a sub 4 was 19 plus 10 gives me 29. So there's your next term. So you have to know the previous term. That's basically what this is. A sub n minus 1 is really means previous term. Okay. Next one is another recursive. A sub 1 equals 1. A sub 2 equals 1. And so I already have my first two terms. So if I want to find a sub 3, I'm going to do the same thing I did before. I'm going to put a 3 in here, a 3 here, and a 3 here. So a sub 3 is a sub 3 minus 2 plus a sub 3 minus 1. So that's a sub 1 plus a sub 2. Well, I already know what my a sub 1 and my a sub 2 are. 1 plus 1 gives me 2. So that's my third term. My a sub 4, we're going to kind of do the same thing. Just plug it in. We're going to plug in 4 into this n, 4 and 4. So a sub 4 minus 2 plus a sub 4 minus 1. Well, 4 minus 2 is 2. 4 minus 1 is 3. So this is saying put in my second term, which is 1, and then my third term, which is 2. So it's going to give me 3. So you can kind of tell looking at it, if I want to find the third term, I'm taking the first and the second. If I want to find the fourth, I'm taking the second and the third. You're taking the two previous terms. So I'll do one more this way, and then I'll do one more with a pattern. A sub 5 is a sub 5 minus 2 plus a sub 5 minus 1. So that's a sub 3 plus a sub 4. That will give you a sub 3 was 2. A sub 4 was 3. Oops, let me make this, let's erase that. Let's make this red. So you can see you're doing the previous terms. So I only asked you to find the next three terms, but if I wanted to find more, basically add the two previous terms. So 3 plus 5 is going to give me 8. 8 plus 5 gives me 13, and I can keep going. Okay. So the recursive sequence that you just generated is the first 5 terms of the Fibonacci sequence. Fibonacci numbers are named after Leonardo of Pisa, known as Fibonacci. And his book, Liber Abaci, it introduced the sequence to Western European mathematics. Although the sequence had previously been described in Indian mathematics, the numbers from the sequence are found in numerous places in nature and are related to the golden ratio. So that's just Fibonacci sequence. Okay, so convergent and divergent series. If your terms approach a specific number, it's called a convergent sequence. Kind of like you converge in traffic, you merge in traffic into one lane, you're converging into one number. If your terms do not approach a specific number and appear to get larger to infinity or negative infinity, they're called divergent. So let's go ahead and do these. If you look at problem example 5, a sub n equals, a sub n equals negative 3n plus 12. That's a linear function. So before we even do it, you should probably know whether that's convergent or divergent. You can probably figure it out, but we're going to do it anyway. So all we're going to do is some substitution. You're all going to start off with your n as 1, first term, second term, 3, 4, 5. And if I plug them in, negative 3 times 1 is negative 3, plus 12 is 9. Negative 3 times 2 is negative 6. Negative 6 plus 12 is 6. Negative 3 times 3 is negative 9. Negative 9 plus 12 is 3. Negative 3 times 4 is negative 12. Negative 12 plus 12 is 0. Negative 3 times 5 is negative 15. Negative 15 plus 12 is negative 3. So we're just substituting these in, and we're graphing. And when you plot these points, you don't connect them. It's a sequence. They're just numbers. We're not going to do 1 point fifth term, 1 point fifth term, 1 point sixth term. You're doing 1, 2, 3, 4, 5. So they should say as coordinates. So we've got 1, 9. Actually, let me make this one bigger. 1, 9. 2, 6. 3, 3. 4, 0. 5, negative 3. Okay, and so when you look at that, and if I look at my x values, oops, I didn't mean to do that. I meant to use the arrow. If I look at these values, if I keep going up, these are going to keep getting smaller and smaller and smaller and smaller. They're going to go on forever. So this basically is a divergent series, so it diverges. Okay, next one, we have a recursive formula. So our first term, so we're going to start with 1, 2, 3, 4, 5, 6. So our first term is 36. So this basically says my second term is 1/2 of a sub 2 minus 1. So it's half of the first term. So half of 36 is going to give me 18. If I do the third one, that's going to be 1/2 of a sub 3 minus 1. Half of a sub 2, you're doing half of the previous term. So then half of 9 is 4.5, half of 4.5 is 2.25, half of 2.25 is 1.125. So again, if I, oops, let me fix my pen. Okay, so if I want to plot these, this might be a little bit harder. Actually, let me use this one. So I've got 136, oops, 136. That's not very good. Let me do a thicker pen. Okay, so I've got 136, 2, 12, 14, 16, 18, 3, 9, 2, 4, 6, 8, 9. So I should be in the middle a little bit. 4, 4.5, 2, 4, 4.5. Sorry, and those should be a little bit over, but it's hard to do it with a pen. 5, 2.25, so it's a little bit here. 6, 1.25. And if you keep going, you'll notice that these are getting closer and closer and closer to an asymptote at 0. So this actually diverges to 0.